Thank you. My name is Michaël Melchiore, as was just said. I basically have done the introduction. Thank you. I've been programming data-intensive real-time software for more than 15 years in various fields, the railway, the radar, and the space industry. I started as a professional software engineer in 2008. The same time, this book was first published. So The Art of Multiprocessor Programming. And in the early years of my career, I witnessed and participated in the adoption of multi-core processing targets in the industry. And I think that the title of this book is quite accurate, especially at the time, given the tools that were available to us. You notice it's art, it's not science, it's not engineering, it's art. And when you're dealing with real-time, sometimes safety-critical software, being involved in art is not a really good sign or very comfortable position. So this initial exposure I had to the topic followed me throughout my career, and every time I joined a team, I became sort of the multi-core artist in that team. And with that background, it was only natural that I became interested in Rust. So I discovered Rust in 2014 and tried to bring it to my work ever since. And I succeeded in 2022. So I've known pain, but I'm persistent. Thanks. So the goal of this talk is to share with you why my team is interested in using Rust and what we did to build our case for the adoption of Rust in our industry. So in this talk, you won't be saying any fancy, complicated, advanced Rust. We are more in the baby steps phase, but at least as far as I'm concerned, that's okay, because the first step are usually the most difficult to take. So first, I need to give you a bit of information of the context when you're developing software for satellites. Space first. So satellites operate in space, obviously. Space is a very hostile operating environment. The satellite is subjected to radiation, cosmic particles, electromagnetic fields, huge temperature differences. Secondly, space is very expensive to reach. It literally costs millions to just send a washing machine, trash can in space. So when we design a satellite, the most critical budget we need to satisfy is called SWAP: size, weight, and power. So for a given feature scope attached to a satellite, we need to make it as small, light, and energy efficient as humanly possible. So to satisfy those two constraints, traditionally in the space industry, we've been using very specialized equipment. We call them radiation hardened. And if you want, what you need to keep in mind about that hardware is that it's both extremely expensive and does not deliver a lot. So it's, for example, at the start of the industry, memories were a few kilobytes big. Processors were extremely slow, up to 20 times slower than their counterpart on the ground. And yes, communication links were also extremely slow. So on the right here, you have a breakdown of a typical satellite. In the center here, you have the central processor. That's where most of the onboard software is being executed. You can see that one of the first role of the onboard software is to manage and control all the equipment on the satellite. So for example, you have on the top solar arrays and batteries to generate and store the power. You have on the right sensors and actuators. So that's for controlling the satellite attitude. So typical actuators, you can have thrusters, you can have reaction wheels, for example. And then on the left, you have antennas, which allows communication with the ground. So far, everything I've described is responsible for the possibility and the continuity of flight. Now you need something else to generate scientific or business value. And for that, we have the platform accommodates what we call payloads that are here on the bottom. And payloads are already also have a breakdown for themselves. And we also they also have onboard software embedded, and so we also need to manage the payloads. For example, payloads host instruments. So for Earth observation satellite, this might be some really complicated, expensive camera, and the onboard software is in charge of triggering shots, storing the data until we are in range of an antenna, and downlink the data to the ground. The other role that is often underestimated is linked to the antennas there. Satellites are quite far from us, so they are remotely operated. And we need the onboard software needs to provide everything needed to support remote operations. And this includes supporting investigation in case of failure. The software will only tell to the ground what we plan for. And if it's not sufficient to investigate issues, we're in a big trouble. Okay, so onboard software development, so at Airbus Defence and Space, at least in Toulouse, we develop mainly in C. Some of the functions allocated to onboard software are critical for the satellite or the mission. So that's why we say that onboard software is real-time, is a real-time software. So what this means is that there are some critical functions that is to be executed cyclically to monitor the satellite, and they have deadlines associated to each function. And those deadlines must be met whatever the situation. Otherwise, we risk losing the satellite or the mission. And secondly, it's embedded software. As I said, we use specific hardware with limited resources, and we need to achieve all of that in a very limited budget. And the last point is we control very specialized hardware, I would say peculiar hardware. Each of the equipment we have has specific operating modes, and for all equipment, we need to guarantee at any given time that the operating mode of each equipment is compatible with its operating constraints. And lastly, the satellite is subjected to a lot of punishment, so it means that the hardware do fail, and that's the role of the onboard software to adapt. We have to reprogram it. For example, if a network link is broken, we need to program a backup route. So the consequence of those constraints is that there's a really high quality bar that needs to be met before onboard software is deemed flyworthy. In Europe, we have what we call the ECSS, which is the European Cooperation for Space Standardization, that has formally specified the quality standards that we need to meet. Internally, we also follow the MISRA coding practices that comes from the automotive industry. And so, the challenge we have is that that level of quality is really demanding, and despite significant investment in our C working environment into, for example, static analyzers and automation of unit tests, code coverage, whatever, we are very reliant on manual code reviews. And this creates a recurring cost time where whatever the feature, we have to invest a lot to reach that quality. And so the key problem we have right now is that it's very difficult for us to scale our workflow to the modern space challenges required by our customer. So how do we solve that? Obviously, I'm here. So one of the key solutions we are currently studying is Rust. So in 2023, we partnered with the European Space Agency. What we did is that we picked one of our telecom payload software. We selected a subset of the functions, and we re-implemented everything in Rust. And so the methodology is quite important there because, as you may know, switching programming language is quite a polarizing topic, especially in an industry as conservative as the space industry. So when we organize the study, we focused our efforts into building factual evidence of the potential benefits of Rust. We also, since we have a lot of code reviews, here you have a snapshot of one code review. We get reports from the code reviews, the ongoing code reviews on the C code base, and we tried to demonstrate that problem, is it possible in Rust? And finally, since we wanted to achieve results quickly, we had to pick our battles, and we did not rewrite everything in Rust. We focused on a few business-specific functions. And for example, instead of rewriting a complete execution engine in Rust, we chose to use Bevy. So Bevy is a fantastic piece of software. The awesomeness of Bevy does not fit into a 30-minute talk, so sadly, I'm sorry, I won't be talking much about Bevy. I tried, but not possible. Too many cool stuff going on Bevy. Okay, so here you have a concrete example of the kind of challenges we face right now. Previously, we on Boss Software handled maybe up to a few megabytes of data. Nowadays, we are expected to handle up to, let's say, 500 megabytes of data, up to a few gigabytes. And also the complexity of the features we implement means that we need a lot more processing power than what we had before. And means we cannot use radiation-hardened hardware. Instead, we use, at best, what we call radiation-tolerant hardware, but this hardware will fail in space, on average, maybe once a day. And so we have to mitigate that failure in software. Previously, we relied on the hardware, and that we need to mitigate that in software. So here you have, on the right, you have an example. So here the application software is running a telecom algorithm that has been mapped in a specific location in RAM. And what we do is that we capture that state, we call it the execution context. And we have another module, which is called the data management system here, that in the background will periodically snapshot that state and save it into reliable storage. So here you have a flash device here. And if we reset, then the goal is to at boot to restore that state into RAM so that the application software can start quicker. So this feature itself is not that complicated. The problem is the space context, and especially the quality constraints. We have a few non-functional requirements to meet. First, obviously, the execution context can be accessed and modified concurrently by the two modules. We need to prevent data corruption. But secondly, the flash device here is not your typical flash device. It's a space-grade flash device that has operating constraints. And the first one is that if we want to maximize the lifetime of the satellite, we need to keep it power on as little as possible. And so today, verifying those kind of requirements in a C code base is up to the quality standards of the space industry is extremely expensive. It's a continuous investment. Every time a new feature is developed in the application software, we need to make sure that the design constraints are still satisfied. And so we rely on extensive testing and peer reviews. So that's an example, concrete example. Let's break it down into three pieces. First, let's tackle the data exchange with the flash device. We do not use Ethernet-based networks on satellites. Usually, we use what we call the Spacefire networks. It is standards from the CSS. It's both the specification of the hardware forming the network and a family of protocol to be used on that network. You have on the right a description of the few packet types that you can use on the Spacefire network. There are 5 packet types that you can use. For the purpose of this talk, we will focus on the RMAP protocols. RMAP stands for Remote Memory Access Protocol. It allows devices on a Spacefire network to share states, either storage or to expose their control registers, for example. So you emit commands, read or write, and you receive reply based on the... What is interesting about that protocol is that so there's several packet types. You need to parse the value of the yellow field to compute which packet type you are dealing with. But there's also the structure of the packet, even for a given packet type, is highly dynamic. all the blue fields here are either optional or dynamic in size. So it can be quite complex to parse that reliably and efficiently. So in my department, to meet a new requirement about high throughput, low latency data exchanges, we developed a C library, which I think I have on the next slide as an example. So here you have an example of the C library. So basically, we expose a frame object that encapsulates an opaque buffer, and then we expose accessors so that you can get the value of the available field in the packet. And we call the set of fields available and the location in the buffer, we call that the frame metadata. So there's a very simple life cycle to use in C. First, use frame init so that you provide the actual storage to store data in the frame. Then if you're reading data, you can use buffer to provide the buffer pointer to some system call so that the data gets actually written in your buffer. And once you have that, you call parse, which will parse the content of the buffer and compute the location of all the fields and all the derived attributes, such as the packet type and the size of, for example, all the blue fields. And if the parsing is successful, then you can use all the getter and setters defined in the library to get the actual fields content. So, for example, if you're reading the content of first register, the actual content in the read reply is what is in the field that we call cargo. And so you get this kind of API to get the actual value. So first we generated a syscrate, but we use whitelist to only generate the function we are interested in to generate the first level of binding, and then we developed another higher level binding in Rust on top of it. And here, when we designed the Rust high-level API, we tried to solve the typical problem we encountered during the code review on the C library. So, for example, here the metadata fields are truly private. And then, as you cross in the C library, as you cross the function boundaries or the thread boundaries, it might not be clear the state in which the frame object was. So here we use the builder pattern to make sure that first the storage is actually provided, and then we define the equivalent functions of the C API. But parse is defined on the builder object. If it's successful, then only then you get the actual frame object, and then the getter and setters are defined on the frame object. Okay. So once we have that, we could tackle the interesting issues. For example, as I said, we are now dealing with a lot of data. So for example, a given function can handle hundreds of RMAP frames simultaneously, and frames can be 4 kilobytes each, which quickly adds up. So we had a developer that tried to reuse a single buffer across several frame objects, and you see where it is going. So here, for example, the goal of the developer was to compute the new desired value of a register. So that's why here we have a write command with the desired value of the register. And he wanted to compute the value of that register based on the previous reply he received. And the aim was to copy that data in this one. The problem is since those frames reuse the same buffer, if the developer first set the reply address of the write command frame, then it was actually overwriting the data here. So that's a simple example. There are more complex use cases, and that's actually the nice case, because here you have an immediate problem. You can see it right away that you're actually corrupting the content of a buffer. So obviously in Rust, this is not possible. First, owned and shared buffers are different types in Rust. So this means that in terms of API, we can build different API to correctly handle the differences. And you can see it here. the actual buffer that is used in the builder is an enum, and we model, is the buffer shared or owned? And so this kind of practices helps the library developer. But then in terms of API that we expose to the users, if he's using own vector, then he has all the simplicity attached to owning the buffer. If he's using the shared buffer, then all the APIs here model use borrowing, and so we can rely on the Rust compiler to carefully prevent data corruption. Okay, so we have the first block. We can now efficiently exchange our map frames on the Spacefire network. Now, let's get back to the requirements. We need to manage the flash device. We need to power it on automatically. Let's try to do that together. So what we did is that we first created a type, flash session, to model an active session with the flash. The goal is that in the application, there are as many active flash sessions as necessary. We define the APIs to interact with the flash only on the flash session type. The goal is to restrict the interaction. Okay. Then we need another type we call it the flash endpoint, to create new sessions. Okay. Now, remember, we want to control the life cycle of the flash, which means controlling the life cycle of flash session. So since flash interactions are typically long-lived in application, they are done in dedicated background threads. So the solution I'm about to show use cross-beam channels. Okay. So what we did is first, so we defined an event, flash session event, that tracks if a session is being created or finished. Then in the new session implementation, we emit the flash session created event, and then we implement the drop rate on the flash session. When it is dropped, we automatically emit the finished event. And once we have that, the only remaining piece of the puzzle is we need some function that will be called periodically by the onboard software that will process all the received flash session events, and based on the current number of active sessions and the state of the flash device, will trigger a power on or a power off. So if we go back to the first slide when I was talking about the art of multiprocessor programming, for me this is not art. This is simple. This is a simple 5-step recipe. And in the space industry, we're really interested in this kind of stuff. Here we rely, the most unique feature first we rely on is the lifetime analyzers, so that we know that the Rust compiler will automatically insert call to the drop function of the flash session once detected that object is no longer necessary. And the API exposed to the user is really simple. The actual complexity of managing the flash device is completely done away in the application. And even better, this kind of solution actually scales to the implementation of the other part of the puzzle, which is managing the execution context and preventing data corruption. So here we have a similar design. So the goal for the execution context is to model that sometimes some function needs temporary exclusive access to the execution context. So how we do that? What is the new ingredient that we need to inject in the API? The first one is just the option type. We wrap the execution context in the option type, which expresses in the API that this data might not be available every time, every cycle. And so what we do is that when we create a session that required exclusive access to that field, to that data, we just take the data, which replace that value with none, and we get ownership of the data, and we can, for example, move it in asynchronous threads. And similarly, when the session is no longer needed, we take the data back, we send it to an event, and then we restore it in the resource here. Okay, so the first new ingredient in the recipe is the option type. The second one is when you're trying to prevent data corruption, you need to track the pointers that are live in the application. And in C, it's really, really difficult because the pointer is just a number that you can copy around everywhere, and we rely on code reviews to track that. In Rust, we have references that are tracked by the compiler, and we know that once a function call completes, unless it has taken ownership of the data, there are no longer any available live references to the data. And so that's the second ingredient we use. And so the key takeaways, we were really impressed by the simplicity of the concept, because we still believe this is simple in terms of PI and concept. And those concepts compound with each other and allows us to solve traditionally complex issues in our field. And here, so first, the actual features is really interesting and useful, but all the verification burden that we had to bear ourselves has been transferred to the compiler. And the developer experience is nice and fun. So where am I on term? Okay. So yeah, in conclusion, the talk was titled Initial Momentum. Did we achieve significant initial momentum in Rust in my department? The answer is, I think, yes, I was allowed to come. But Rust, as far as I'm concerned, forms a really promising framework for modern on-board software development. So I did not talk about it much, but the development experience, the tools, Cargo and RustNL and so on, are really top-notch. We've also demonstrated as part of this study that we are able to leverage our existing C assets. You don't need to start from scratch. It's usually a bad idea, especially in a field where you have so many quality constraints. But then we were really impressed by the type system, because when Rust claims that it allows everyone to build efficient and reliable software, everyone here is really the key, because the Rust language designers use the ownership, the lifetime analyzer to tackle the memory safety issues. But then everyone can also reuse the same concept to tackle business-specific issues. So, for example, managing the power state of the flash or the data corruption issues on the execution context. So everyone can use the same context to inject their business constraints in the type system, so that the compiler can check those constraints. And if it compiles, then you have the guarantee that your non-functional requirements are met. So I did a little experiment. You can see on the right here in this diagram. I asked several senior experts in my department to estimate the cost benefits of using Rust in our department based on the result of that study. So the bride is me. When you drive change, it's important to manage expectations. But my fellow colleagues were really impressed by the results, especially on the verification front. As you can see, they estimate that we can gain as much as we can cut our cost in half, in the best case. So yes, we will continue invest in Rust. I'm still on time. We have identified a few upcoming activities. The first one is, yes, we've estimated that there will be significant gains in using Rust for existing features, but we also believe that Rust unlocks new features for on-board software development, and so we intend to explore that, especially since we are currently working on constellation satellites that have distributed stakes that we are not used to tackle. So that's interesting. The second upcoming continuing activity is that we've been monitoring performance from the start. The current figure we have are acceptable, but we need to work on them better because that's a complex topic. We hate micro benchmarks in my field. So we need to be more representative. So we need to implement more features, study the system under heavy load. This requires time, and we also need to understand better what we are doing, especially when using a subset of BV, which we are replacing gradually. In terms of enablers, where we are currently we are exploring partnership in Europe, and we are interested in volunteers to work together with us. So we are using a dedicated hardware, which is not currently supported by Rust. We also use specific real-time OS. So in Europe, we will use a lot Artems, which does not support Rust. So there's ongoing initiatives about that. And the other point is that the ecosystem of Rust is really blossoming. We need to help it mature. And again, we want to support that. And the good news is that there's an ongoing initiative about that, Ferrocin, and we are really interested in that. Thank you. I'm on time.
Excellent. So now it's time for questions. We got 10 minutes. I see a bunch of raised hands there.
Oh, okay.
Yes. It's very important in the type of software that you built, the correctness of the code. So I was wondering about tools, formal verification tools that use SAT solvers, for example, to prove the correctness of the code. Is this something that you use? And do you have any thoughts about the state of formal verification in Rust?
So we have, regarding the schedulability of the software, prove that we meet our deadline. We have, in the case for one core target, we have an actual solver that actually proves the schedulability of our software. For other topics, we currently don't use much. We need first to improve and create our database, our code base in Rust, and then we are interested in this kind of tools. We've looked at Kani, for example, and the other tools. So yes, we are interested in that, but it's maybe a bit early.
Thanks for your talk. You mentioned you did an analysis of an existing code base, existing database of code reviews. I can guess a little bit like what kinds of things you would be prevented by coding in Rust instead of C, but what are the classes of errors that you found that you can't, that are still sort of an issue with Rust? Like, what kind of categories broadly would those be?
So what kind of errors can we prevent in Rust? Can't?
We cannot prevent by going to Rust. So what are the limitations?
Logical errors, misunderstanding of the specification, errors in the specifications, the typical errors we have during integration, misalignment on between the hardware documentation and the actual capacity of the hardware. This happens a lot. When you're dealing with bespoke hardware, every time.
Thank you for your talk. I was wondering, because I noticed you use drop implementations a lot and RAI a lot. Is there interest in linear types, so types that absolutely may not be forgotten from your industry?
Yes, but linear type, so for me, linear type is type that needs to be consumed once.
Yeah, it needs to be consumed, so you're not allowed to forget it or put it in an arc that refers to itself in some way. So, you could have this flash example. You don't want your flash to never turn off again because somehow it's drop implementation that turns it off got forgotten.
Yeah, it's a tool. Linear type are tools. If they solve, I don't have any specific use case in mind right now, but if it solves an issue we have, we will use them.
Let's see, there's a hand there.
And nice to hear you had mostly a positive experience with Rust. So I was wondering, did you have any noticeable pain points when trying to adapt Rust? One that comes to my mind is, for example, how do you deal with panics in this situation?
So we don't use panics first in our code. Yes, it's forbidden. But regarding your talk, I think I anticipated your question actually. So there's really nice material available about this kind of questions. So I put the links here. So Rust is a complex language, especially so in my case, in my department, people have only known C. So the jump to Rust is actually very, very big. So invest in training, and then do not underestimate for me, the technical side of using Rust was not an issue, aside from the lack of support from some of our targets. It's more about the human factors. So helping our developers to adopt gradually the language. So you need to start them working in Rust as early as possible, focusing on concrete use cases. Maybe do not start on the key business software first. Consider the larger environment, the tools, and so on. That's. I think that's what I wrote. Yes.
Any other question? I see a raised hand. Well, there's two there.
Hi, I'd like to ask about the radiation. So, of course, you have the specialized hardware, but are like random bit flips that could lead to undefined behavior not a concern at all, or not an increased concern?
Sorry, I did not catch the question.
So you have radiation space, right? And those can lead to random bit flips. Of course, you have some hardware shielding. Is the shielding really so good that you don't have to care about, or that the probability of random bit flips is not increased at all, and you don't have to care about it?
We always have to care about it, but the frequency of the failures might drop significantly to the point where we don't need to take specific mitigation actions. But we always, first we need to survive to the reset, because it can be quite violent. So it's always a concern. On satellite, you usually have a specific hardware that monitors the state of all the equipment. We usually call it the reconfiguration unit. It monitors the state of the hardware or all the equipment. It receives software alarms and so on, and it can generate any kind of resets depending on the issue.
Well, there's another hand there, and more people here.
Thank you. I saw in the examples you were using things like VEC. So that implies you've at least got a memory allocator, or maybe using the standard library. So I just wondered, what platform were you targeting? Can you share a few details about that?
So for payload, we use ARM-based platform running Linux. So specific custom distribution of Linux, Yocto-based. Yes.
Okay, thank you.
I think here there's a couple of questions more. So we'll go for the last question. I just got a signal from here.
You mentioned the maturity of the ecosystem and referenced ferrocene, so presumably the formal spec of the compiler. Is there anything else in the maturity of the ecosystem that is immature?
There's a lot of crates to choose from, and what we need is a curated list of crates that have support, that are maintained, documented. So this needs funding. We need to work on all that. But that's the kind of stuff we're interested in. I think those ideas are already around.
All right. So just before Alex comes up and tells us what's going to happen next, I have this little present for you.
Thank you.
Thanks for speaking here today. Enjoy it.
Thank you.